Hello everyone and welcome back. We have a few minutes before the official class start time. If you have any questions, you can ask them now. Hello everyone and welcome back. We have a few minutes before the official class start time. I did have a good weekend, thank you. Okay, good morning. Today's lecture is going to be about a concept that you've probably seen before, maybe not formally, but you've thought about it. Certainly, if you're taking COMP2804 or you have taken COMP2804 data structures, these things come up, although they're not formally defined because that's sort of the job of this course. And the topic is random variables. So these are things that we think of, well, the name kind of says it, we kind of think of them as a variable, X is a common name for a random variable, that takes on random values. So it takes on different values with different probabilities. So that's the way we think of them, and it's often even the way we reason about them. But formally, the definition is actually very different. This is the definition of a random variable. So it's not a variable, and it's not random. It is a function from some sample space onto real numbers. Okay, so we're comfortable now working with sample spaces. That's the sets of outcomes from some experiment, and probability spaces, which is a combination of a sample space and the probability measure over that sample space. And a random variable fits into that framework, and the way it does so is it takes each possible outcome and assigns it a real number. Okay? So, and that explains why we think of them as variables, right? Because we run this experiment, we get some outcome in S, and we assign it a real number. So we think of, you know, X, the random variable, gets that number with a certain probability. So for example, one that we've seen before, and this is, we roll 2 dice. So there, the sample space is the pairs ij, where ij are integers 1, 2, 3, 4, 5, or 6. And the probability of any particular outcome is 1 over 36, 1 over the size of the sample space, right? So this is the usual sample space. We roll 2 dice, a first one and a second one. They can take on 36 different possible values, 6 values for the first one, 6 values for the second one, and each of those is equally likely. You know, a random variable that we could define is something like, I'll call it W. You take something in S, so a pair ij, and maybe the value of it is equal to the sum I plus j. So we've studied this before, right? You roll 2 dice, and you take their sum. So you get some number when you do this. You get some number between 2 and 12. Nothing too weird there. Let's look at a few related examples. So let's say we flip 3 coins. Okay. So then we get this sample space, which has 8 elements. All 3 of our flips could be heads. They could be heads, heads, tails, heads. And then finally, so there's our sample space, and the probability space is the usual one. The probability of any particular outcome is going to be 1 over 8. There's 8 possible outcomes, and each of them is equally likely. Okay. So another sample space, and we could look at a random variable x. And we can define it in plain language and say it's equal to the number of heads. Okay. You know, we do this experiment, we get some outcome, and we count the number of heads. So that takes an outcome and maps it onto a real number. In fact, it maps it onto an integer 0, 1, 2, or 3. And if we want to write that out explicitly, that will look like x of heads, heads, heads equals 3. X of tails, heads, heads equals x of heads, tails, heads equals x of heads, heads, tail. That is equal to 2. Okay, so there's the random variable that counts the number of heads in this this thing. You know, we can define whatever we want. Here's another one, y. That we might be interested in studying the particular events where we toss the coin and it comes up the same all 3 times. So it comes up heads 3 times, or it comes up tails 3 times. So this would have, you know, 3 cases. It's 1 if the outcome is heads, heads, heads. It's also 1 if the outcome is tails, 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 and it's 0 otherwise. Okay. So if the outcome is neither of those 2 things. All right. So nothing weird here. This is just definitions. I'll warn you guys today. Unlike many of our classes, we won't have a big surprise at the end of the day. The more exciting stuff comes tomorrow or next class. But still pay attention today, because the definitions are critical for pretty much the rest of the course at this point. So it's important that we understand them. Okay? So we'll go through some, you know, the most basic examples so that it's as clear as possible. And it's also important that we understand, you know, these are the formal definitions, and then we'll somehow use informal language when we talk about random variables. So it should be, I want to make it clear when we use that kind of informal language what it really means in terms of the definitions. So random variables can, you can use them to define events. So for example, here's an event that I might say the random variable x is equal to 2. And formally that makes no sense at all, because x is a function. I can't say that the function is equal to 2. What I mean when I say that is this is the set of events for which I get the value 2 when I evaluate x. So this would be the set. Where do we get the value 2? Well, we get the value 2 for this, this, or this. So that's the the event x equals 2 in plain language, we really mean it's the set of outcomes omega so that x of omega is equal to this thing. So more formally, the event x equals little x is the set of outcomes omega in S such that x of omega is equal to little x. And this is just one example, little x equals 2 with this particular set here. Okay. And of course, once you have events, you can have probabilities. So here, I could say, you could ask, what's the probability that x equals 2? Well, the probability that x equals 2 is the probability of this event, and that is just the sum of the individual probabilities. We've seen that lots of times, and each of those individual probabilities is 1 over 8, so this is just going to be 3 over 8. And you can do that for all the other possible values of x. For instance, the probability that x equals 0. Well, there's only one thing that makes x equals 0. That's tails, tails, tails. So that's 1 over 8. Probability that x equals 1. That's this one. 2 tails and 1 head. So that's has 3 elements in it. That's 3 over 8. And we've seen probability x equals 2. The only one left is probability that x equals 3. That's this one. There's only one event that causes that to happen, so it's 1 over 8. So these random variables define events. These events have certain probabilities. We know how to compute probabilities of events. All right. Well, once we have a notion of events, we've seen that associated with events, we have, I'm a little bit confused, what is the little x? The little x is just any real number that you like. Okay, so here I showed you this for little x equals 2, little x equals 0, little x equals 1, little x equals 3, right? So pick a number, presumably one that the random variable can take on, and then you can compute the probability that it takes on that value. Okay. Hopefully that's clear. What is y of omega? Where do you see y of omega? Here. That's this random variable that I've defined called y, that somehow is equal to 1 when all 3 coin tosses are the same, and it's 0 if they're not all the same. So you can define a random variable however you want, as long as it takes every outcome and maps it onto a real number. So this takes these 2 particular outcomes, all heads and all tails, maps it onto the number 1, and everything else maps onto the number 0. All right, good. Okay. And we can do the same thing for y here. So y takes on 2 possible values, 1 or 0. So we can look at, the probability that y is equal to 1. Well, that's just the probability of this outcome, heads, 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 or this outcome, tails, tails, tails. Each one of those occurs with probability 1 over 8, so that gives us 2 over 8. And the probability that y is equal to 0, well, we can either count these up. So list out the ones where y is equal to 0. And in fact, that's easy. There's 1, 2, 3, 4, 5, 6 of them. It's everything except these two. So that's going to be 6 over 8. And if you didn't like that, if it takes too long to count to 6, then you could say, well, y only takes on two different values, 1 and 0. We know the probability that it takes on 1, and so therefore by the complement rule, the probability that it takes on 0 is 1 minus the probability that it takes on 1. So 1 minus 2 over 8 is also 6 over 8. Okay, good. But that only works because of the y is a binary random variable. It only takes on two different values. And more generally, if it takes on k different values, if you know k minus 1 of those probabilities, you can compute the last one because they all have to add up to 1. Okay, so let's here's a definition. Two random variables x and y are independent if for every little x, little y, so every pair of real numbers, little x and little y, the probability that x equals x and y equals y is equal to the probability that x equals x times the probability that y equals y. Okay. So remember, we have this idea of we can define events in terms of random variables. Events are just sets. And so if I say x equals x and y equals y, this defines a set, this defines a set, and the and is the intersection of those two sets. So basically this is an event, this is an event, and they're independent if the probability that both of those events occur is equal to the product of the two probabilities. So it's almost like our definition of independence for pairs of events, except that a random variable x defines many events, right? Here there were 4 different possible events for this random variable x, 0, 1, x equals 0, x equals 1, x equals 2, or x equals 3. So we have to check this definition for every pair of events. So that's what it means for two random variables to be independent. It means I can define an event with one of them, I can define any event with the other one of them, and the probability that both those events occur is just the product of the two probabilities. So that's bigger, that's somehow a bigger job to check independence of random variables than it is to check independence of events, because you actually have to check a whole bunch of different possible events. You have to look at all the possible values x can take on and all the possible values y can take on, and then check that this is true for those things. So we could look at, we have two random variables defined on the board here in some probability space. So we could ask if they are independent or not. And if we want to prove that they're independent, then we would have to try all the values for x here and all the values for y here. So we would have to try 8 different possible values and then check that this is true for all 8 of those possible values. So all 4 values for x and both values for y, and check that this is true. Now, thinking about these random variables, if we take a step back, one of them counts the number of heads. X counts the number of heads, and y is 1 if all the coin tosses are the same, and 0 otherwise. So it feels like these two things should not be independent. And the nice thing about that is if they're not independent, then all we have to do is find one counterexample, one little x and one little y, for which this equation doesn't hold. And, well, here's an example. If all my coin tosses are the same, so that means y equals 1, then my coin tosses, I cannot have 2 heads, right? If all my coin tosses are the same, that means I either have 3 heads or I have 3 tails, so 0 heads. So if all my coin tosses are the same, I can't have 2 heads. So that suggests that I should be able to just look at the probability that x equals 2 and y equals 1. Well, that's just the probability of x equals 2 is this set. And y equals 1 is this set. Now, this set and that set have nothing in common, right? If I take the intersection of these, there's nothing in common, so I get the empty set. So that's just equal to the probability of the empty set. And the probability of the empty set is 0. And 0, well, it's not equal to 3 over 8 times 2 over 8. And why did I mean, that's obvious. Why did I pick these two things? Well, that's because 3 over 8 is the probability that x equals 2, and 2 over 8 is the probability that y equals 1. So probability x equals 2 and y equals 1 is not equal to the probability that x equals 2 times the probability that y equals 1. Therefore, x and y are not independent random variables. All right. Good. So that's an example of random variables that are not independent. Let's see if we can define some that are independent. So let's define a third random variable. Z is 1 if the first coin is heads and 0 otherwise. So Z is the random variable that really only looks at the first coin and counts counts 1 if it's ahead and 0 if it's not. So more formally, we would have z of omega is equal to 1 or 0, and it's 1 if omega is in the set heads, tails, tails, heads, tails, heads, 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 tails, and heads, heads, heads. And it's 0 otherwise, which is the same thing as starts with tails. Tails, tails, tails. Okay, so 2 ways to define z. 1 if the first coin is heads, 0 otherwise, and we can explicitly write out the sets for 1 and 0. These are all the ones that start with heads. Not surprisingly, there's 4 of them. That's half of the possible outcomes. And there's 4 of them that start with tails. Also half of the 8 possible outcomes. So now let's look at these random variables, z and y. Are they independent? So just by quick inspection, if I had to guess and didn't know anything about this, I would guess no. And why would I guess no? Well, I would guess no because the value of z depends on this first coin toss, right? It's either heads or tails, and the value of z is determined by that. And the value of y depends on all 3 coin tosses. So it seems that these 2 things should be related. Like it feels like they should not be independent because they both depend on the same thing. They both, as part of their definition, each of them relies on the outcome of the first coin toss. So that's what our intuition tells us, that maybe they're probably not independent. But of course, we can't trust our intuition here. We have to go back to the definition, and the definition says they're independent if you check for every possible pair of outcomes. 1 for x, or in this case 1 for y and 1 for z, whether this formula holds. So we'll just have to check that to see if it holds. So let's do that. So probability that we're interested in y and z. So let's start with y is 0 and z is 0. The y is 0 events, there's 6 of those things. So that's the y equals 0 event, and the z equals 0 event, that's this one. That's all the outcomes with tails. So what is the intersection of those 2 things? So what we're looking at is the ones that in here that start with tails. That's this one, and this one, and this one. All of those appear over here, and none of those do. So that's probability of tails, heads, heads, tails, heads, and tails, 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 heads. That's 3 out of 8. And let's compare that to the probability that y equals the product of those two probabilities. So we put a question mark here. Is that equal to the probability that y equals 0 times the probability that z equals 0? Well, the probability that y equals 0, it's gone now, but we computed it. It was 6 out of 8. And the probability that z equals 0, that's easy. That's 4 out of 8, or 1/2. And so, indeed, that is 3 out of 8. Okay. So, that is correct. The probability y equals 0 and z equals 0 is equal to the probability that y equals 0 times the probability that z equals 0. So that passes the test for independence, but yeah, guest lecture from Cat. No, I don't want to pick up the cat. Maybe it'll show up again. Yeah, so that passes the test for independence, but it only passes it for one of the choices for this and this. We still need to check 3 more of those possibilities. And if we do that, we'll find the probability, so we can do probability y equals 0 and z equals 1. We're going to get, if we do exactly the same thing we did before, we still have the same y equals 0, but now the z equals 1, that is, all the outcomes here start with heads. So when we take the intersection, we'll just get these things. It's the ones that start with heads. So we'll get 3 out of 8 again. And that is, again, 6 out of 8 times 4 out of 8, which is equal to the probability that y equals 0 times the probability that z equals 1. So that one passes as well, and then we have to check the probability that y equals 1 and z equals 0. So y equals 1 means we get one of these two outcomes. Heads, 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 or tails, tails, tails. And z equals 0 means we get an outcome that starts with a tail if I take the intersection of those two things, well, I only get this one, right? And 1 over 8 is equal to 2 over 8 times 4 over 8, which is equal to the probability that y equals 1 times the probability that z equals 0. And then finally, if I do the same thing y equals 1 and z equals 1, I'll get that this is equal to the probability of heads, heads, heads is equal to 1 over 8 is equal to 2 over 8 times 4 over 8 is equal to the probability that y equals 1 times the probability z equals 1. Okay? So it's a bit of a painful exercise, but if we do it, we'll find that y and z, despite our initial intuition, y and z are independent. Right. So therefore, y and z are independent random variables. Okay, so someone says if you remove heads, heads, heads from the event y, then it will be not independent. Yes, that's probably correct. So if y is only 1 when you get all tails, then you'll be able to find a counterexample. In fact, yeah, the counterexample is the 1, 1, because then you could never have y equals 1 and z equals 1. Y equals 1 would mean all tails in that case. Z equals 1 would mean first one is heads. So that means the probability of both of those happening is 0, which is not the product of their individual probabilities. But for this definition of y and z, these things are independent. So unfortunately, proving that two things are independent, unless it's given somehow as part of the problem statement, for random variables, it gets long, right? This is just 2 random variables, and they're binary random variables, so there were only 4 outcomes to consider. And this is already a boring exercise. Now, if we wanted to do this with, well, we had this random variable that counted the number of heads, x. If we wanted to compare that with z, we'd have to look potentially at 8 things, or quickly find one that's not true. Okay. And I will just write it here, but we won't deal with it much. It's just important that you know it. Okay. So we saw the definition of what it means for 2 random variables to be independent. What if you have more than 2 random variables? Well, we saw that already that is an issue even if you're talking about events and not random variables. There's somehow 2 different definitions, so let's write that down. Definition, sequence of random variables. X1 through xn is pairwise or mutually independent if for every little x1 up to a little xn real numbers, the probability that x1 equals little x1 and so on, and xn equals little xn is equal to the product of those probabilities. No, I shouldn't say that. That's not a good way to do it. Let's say the events x1 equals little x1, x2 equals a little x2, up to xn equals a little xn are pairwise or mutually independent. So, right, this definition up here says if you give me two random variables, then any two events that I can define with them should be independent. If so, then these guys are, those two random variables are independent. And this one says if you give me a whole bunch of random variables, then any n random variables, that means I can define n different events, one involving each random variable. That thing should be, well, if you want to claim that the random variables are pairwise independent, then those events should always be pairwise independent. And if you want to claim that they're mutually independent, then those events should always be mutually independent. To check if two variables are dependent, can we check them with the conditional probability formula? Well, so be careful, because the conditional probability formula requires, so it's about the probability of A given B, requires that the probability of B not be equal to 0. So if you want to use that formula, you have to, you always have to be careful that that B is not 0. And actually, if you look very closely at the definition here, that means you need to rule out something. So just going back to the definition of independence for two random variables, this says I need to check for every x, y real numbers whether this is true. And you might think, well, hey, you cheated then, because you only checked for x and y equal to 0 and 1. What about, 0.5 or x equals to pi, y is equal to 1.9. You didn't check all of those things. Well, even though this says you have to check it for all real numbers, if you pick either of these numbers to be a value that that x or y never takes on, then of course you get a probability of 0 in the corresponding thing over here, and you get a probability of 0 in the corresponding thing over here, right? So you get, this will be 0. So one of those events defined by that will be the empty set, which has probability 0. So you're multiplying 0 times something. And this will be the empty set, because it's the intersection of the empty set with something. And so this formula works fine even with 0 probability events. The conditional probability formula doesn't, because then you're dividing by 0. So always better to use this, this definition of independence. Yeah, so this says these events, x1 equals x1, so I even put quotes around them to indicate that these are these events defined informally this way, that they should be pairwise independent, or they should be mutually independent. So whichever one you're trying to prove. If you want to say the random variables are pairwise independent, then the events should be pairwise independent. Is there some rule we can follow to make intuition? This takes forever. No. In general, there's not a simple rule that tells you when things are independent and when they're not. Sometimes it's there in the problem statement, and you are rarely asked to prove, we won't ask you to prove that things are independent if it's not in the problem statement and it requires you doing a million calculations like this, I just want you to realize that there are things which appear not to be independent, like Z and Y in this example, that for whatever reasons do work out to be independent. So don't assume that things are not independent. In general, if you don't know, then it's okay. You just assume that they're not independent, and don't that never hurts you. Just when they are independent, there's some nice things you can do, but when they're not independent, you just can't do those. You have to avoid assuming that. All right. Okay. Now we get to the whole purpose of random variables, which is to study their expected value. So again, a definition. The expected value, and sometimes people call this the mean of a random variable x so we write it this way, e of x, and it's equal to the sum over omega in the set of outcomes of the value that the variable takes on for that outcome times the probability of that outcome. Okay. So I have my set S of all possible outcomes. I walk through it for each of those outcomes, omega. I evaluate x, and I multiply it times the probability that that's my outcome. And it's not too hard to see that there's another way of doing that, which is you sum over all the values x of the probability that big X equals X times X. So this sum here, just you imagine it as going through each element of your outcomes and summing, summing these things up. This sum here, you just think of it as, well, let's look at my outcomes where the value of this thing is equal to some x, and compute that probability and multiply it by x, and then maybe this is x1, and then there's another variable value x2 that they could take on. These are the outcomes where it takes on x2, do that. It's the same sum in either case, it just, you imagine it groups them together differently. Okay. So yeah, so that's the definition of the expected value. And you may also see this called the mean, sometimes the first moment. There's different names for it. Some people, usually non-mathematicians, might call it the average. I don't like average because it has other meanings. But it's the name we'll use is expected value, sometimes expectation, but just be aware that there's other names for this thing. So, for example, we could look at tossing a coin. and we count a 1 if we get a head and a 0 if we get a tail. And this is the usual coin sample space, heads, tails, and the probability of any outcome is a half. And we look at the expected value of x. Well, we need to sum over all of the outcomes. So let's do that. That is, let's take the first outcome is heads. So we get x of heads times the probability of heads plus x of tails times the probability of tails. This is equal to x of heads is 1. Probability of heads is 1/2. X of tails is 0. The probability of tails is a 1/2. And so that equals 1/2. Okay. So if I assign a 1 to one side of the coin, the head side, and a 0 to the other side, then the expected value that I see is 1/2. And that kind of makes sense, right? So think of if I did this experiment many times, then somehow on average, if I averaged over all those experiments, if I did it n times, I kind of expect to see n over 2 heads, right? That's sort of what you would think. Okay. Another one is to roll a 6-sided die. So there, that's this sample space again. Just one this time, just one die. The probability of omega is 1/6. And let's say that we'll define the random variable x of I is equal to I. So if I roll a 1, the value of the random variable is 1. If I roll a 2, the value of the random variable is 2, and so on. So it's just the number that comes up. Well, then you get that the expected value of x, we have to sum over all of the outcomes times the value of that outcome, which is just the outcome itself. So we get 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6, which works out to 3.5. Or if you don't like that, 7/2. Okay. So again, this is another case where maybe the name of this thing is not the most well-chosen thing. So we saw that a random variable is a function, so it's not random and it's not a variable. And now we're seeing that the expected value, which you might think means the value we expect to see when we roll a 6-sided die, is the value 3.5. So it's a value that never actually occurs, but yet it's the expected value. It's just the definition. So maybe it's a poorly chosen name, maybe not. Just keep in mind that expected value doesn't mean a value that you might actually get, because of course you never roll a 3.5, but somehow on average that's the number that you see. And you can define other other things. So same sample space, same probability space. You could define random variable yi is 1 over I. So there, instead of taking the value that's on the die, you take its reciprocal, 1 over that value. And if you do that, you can ask, what's the expected value of y? Well, that's going to be 1 over 1 times 1 over 6 plus 1 over 2 times 1 over 6 plus 1 over 3 times 1 over 6, and so on, all the way up to 1 over 6 times 1 over 6. And if you work that out, you get 49 over 120. Why this value, why this particular random variable, I don't know. Maybe as part of some role-playing game, this represents something, some damage that you incur when you enter a battle. You roll a die, and the damage is 1 over the value on that die. 1 meaning that it's all your health, you die immediately. 2 meaning it's half your health. 3 meaning it's a third of your health, and so on. Who knows? Whatever you want. Okay. Do another quick example, and then we get to the main lesson and the most important thing you will learn about random variables, probably for most of this course. It's something that I use all the time, so we're getting to it. Let's go back to this thing we saw early on, rolling 2 dice. So that's the set ij, those ij in 1 through 6, and the probability of any particular outcome is 1 out of 36. And we'll take the random variable x, which takes the 2 dice, I and j, and adds them up. So, okay, we want the expected value of this. Well, we see that there's actually 2 equivalent definitions. There's this one where we sum up over all of the possible outcomes in S, the probability of that outcome times the value of that outcome. And then there's this one where we sum up over all the possible values, the probability that x takes on that value times the value itself. So if we do this one, well, first let's notice that the probability of each individual outcome is 1 out of 36. So we can take a shortcut and just realize that all we need to do is add up all of these values that we get, but we still have an issue that there's 36 of them, right? I mean, there's 36 possible outcomes when we roll 2 dice, and so we have to map them, figure out all of them. So we'll get some, if we do this, we're going to get some sum that has like, it'll have a 2, and it'll have, well, I can tell you, it's going to have 3 and another 3, and it's going to have a 4, 3 4s, and 5 5s. It goes on for a while, and you know, it finishes with something like there's 2 11s, and then there's 1 12. That seems painful, because there's 36 things to add up there. But if we do it, carefully and correctly, we'll get an answer, and that answer will be 7. So that's not great. That's what happens if we use this definition. We could try the equivalent definition. And if we do that, then we don't get this, not all these probabilities are the same, so we can't just multiply everything by 1 over 36, but we only have, the only possible outcomes for this random variable are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's only 11 possible outcomes. So at least we don't have to deal with 36 terms. And if we do that, we'll see, we can start this. How many ways are there to get a 2? There's 1 out of 36 ways in which we get a 2. We roll 2 1s. How many ways are there to get a 3? There are actually 2 out of 36 ways to get a 3. We can roll a 1 and a 2, or we can roll a 2 and a 1. So that gives us 2 out of 36. How many ways are there to roll a 4? Well, we can use actually the same reasoning. That gives us 3 out of 36. And a 5. There's 4 out of 36. And a 6. There's 5 out of 36, and a 7, and there's 6 out of 36 ways, and an 8, there's 5 out of 36 ways, and 9 can happen in 4 out of 36 ways, 10, 3 out of 36 ways, and 11, 2 out of 36 ways, and then finally a 12 can happen 1 out of 36 ways. And if we add all those up carefully, we better get the same result, which is a 7. And actually you can kind of see this here, right? There's the 2 that came 1 out of 36 ways. There's the 2 outcomes that give us 3s that happen, 2 out of the 36 ways, and there's the 3 outcomes that give us 4. So we get the same answer in either case, but neither of these is particularly nice, right? Both of these are painful. So surely there's got to be a better way, and if we step back and look at everything that's on this board, we might have guessed this without doing this calculation. And why might we have guessed this? Well, we might have guessed this because over here we did this calculation that said when we roll one 6-sided die, the expected value is 3.5, or 7 halves. So if we roll 2 of them and add them together, then it makes intuitive sense that the expected value should be twice as much. So instead of 7 halves, it should be 7. And indeed, that's the case. Now, the question is this just intuition, or is this something that is true in general? And the answer is, it's true in general. So there's a property of expected value called linearity of expectation, which tells us that this is always the case. It says for any two random variables x and y, the expected value of x plus y is equal to the expected value of x plus the expected value of y. Okay? This is the most important thing there is to know about random variables. It's the thing that we will use over and over again to solve all kinds of problems and determine expected values of very complicated looking random variables. Okay? So we'll almost never have to do this kind of nightmare just by using linearity of expectation. Okay? So for example, here, so let's be first clear. What is this x plus y? Well, this you can think of as, this is a new random variable z defined by, for every omega, z of omega is equal to x of omega plus y of omega. Okay. So when I add together two random variables, that's really defining a new random variable that says, well, if you give me the outcome omega, then that random variable has the value x of omega plus y of omega. Okay? And then that just says that that's equal to the expected values of these two things. So just like what you would think. And so here's how you tackle this thing using linearity of expectation. You say x1 of ij is equal to I, x2 of ij is equal to j. Right. This is the value that you get when you roll the first one. So you roll two dice, but you only take the value of the first one. This is you roll two dice, but you only take the value of the second one. And then you notice that actually x is equal to x1 plus x2. This x here takes the sum of the two, so this random variable x is the sum of these two random variables. And now you apply linearity of expectation, which says, therefore, that the expected value of x is equal to the expected value of x1 plus the expected value of x2. And this is basically what we already computed. If you want to go through it carefully, you'll realize that you get a bunch of things. They're all multiplied by 6 out of 36 instead of 1 out of 6. But you get the same thing. So you get 7 halves for the first one and 7 halves for the second one. So you get 7. So basically, calculation free, just as long as you know the simpler random variables, x1 and x2. So this linearity of expectation is super useful for a couple of reasons. So one is it lets us take a complicated random variable and break it down into simpler pieces, ones whose expected value are hopefully easier to compute. And we'll see next class that this is a trick that we do frequently, and we often break it down into the simplest pieces imaginable. So we can, many random variables, we can break down into a whole bunch of binary random variables. So random variables that are just 0 or 1, called indicator variables. And their expected values are really easy to compute because there's only 2 terms in this this sum. If the size of S is 2, then this is kind of an easy thing to do. So that's, it's useful for this sort of divide and conquer approach to computing expected values. But the critical thing, and don't forget this, is I've underlined it here, and I'll underline it and box it again. This is true for any two random variables, x and y. So in particular, I don't care. It's true even if x and y are not independent. So x and y can be two things that are closely related to each other, really intertwined. I don't really understand the dependence between them. It doesn't matter. This is still true. Okay. That's what makes this so powerful, is that we don't have to worry about independence to use linearity of expectation. All right. And of course, if there's a version of this for two random variables, there must be a version for a whole bunch of random variables. And indeed, for any sequence of random variables, x1, x2, and so on up to xn, the expected value of x1 plus x2 and so on up to xn is just the sum of the expected values. And again, I'll highlight any sequence of random variables. It does not matter if those random variables are independent or not. That's what makes this so useful and so powerful. Okay. And if you want the proof of this, it's trivial. So I'll just prove this one, not the second one. So expected value of x plus y. Well, x plus y we said is this thing here, right? So this is really talking about the expected value of this z. So we have to sum up over omega in S, z of omega times the probability of omega. Well, z of omega, that's the definition of it here. This is just the sum over omega in S of x of omega plus y of omega. And then we multiply that by the probability of omega. But this is just the sum of x of omega times probability of omega. Plus, so we split the sum into two. Again, we sum over omega y of omega times probability of omega. But wait a minute, this is just the definition of the expected value of x, and this is just the definition of the expected value of y. So that's the proof that you have that random variables have linearity of expectation, right? You basically just apply the definition of what you meant when you said x plus y. Well, you meant this random variable z defined this way, and once you do that, you get two sums, one of which is equal to the expected value of x, and the other one is equal to the expected value of y. So the proof is easy. But it's an incredibly useful thing. So next class we will start making use of linearity of expectation to analyze all kinds of interesting random variables. So random variables that have to do with running times of algorithms, well, and a whole bunch of cool things. So this class was a bit of a grind getting through the definitions and making sure we understood them, but the important thing today is from those definitions follows a very simple but powerful thing, which is linearity of expectation. That's the main thing you need to remember from today. Okay, so that's a good place to stop. If anybody has any questions, you can ask me for the next couple of minutes. Would it be possible to quickly go over the expected value of x1? You mean this thing here? So this just says, this is just the general version of this one. So this says for two random variables x and y, the expected value of the sum is the sum of the expected values, and this just generalizes it to a whole sequence of random variables. And if you're wondering what this means, well, this is the random variable, again, I'll call it z, which if you give me omega, it gives me x1 of omega plus x2 of omega, and so on, all the way up to xn of omega. So formally, remember, these are functions, and when we say we add them together like this, we mean for each possible input, the value of the sum for that input is the sum of the values of the individual functions. Hopefully that's what you were asking about. Good. So probably like many of you, the cat slept through the majority of the lecture. So it's not, the cat's not really working for me as an active audience member that I was hoping that she would be. All right, so I will see you on Wednesday.